Is it visible? And am I audible to all of you?
Yes,
Yes,
sir.
sir. Thank you, everyone. And a very good evening to everyone who joined for the FTP, ATL FTP. And first of all, I wish to thank Dr. Saranya and Park Institutions for having me for this ATL FTP and the technical team who had me connected with this team. Thank you so much, everyone, for the invite. And today's agenda is to discuss the forward propagation in RNN. And I like to move ahead. Beforehand, I like to discuss a few couple of things why RNN and few fundamentals related to RNN, and we'll move ahead with forward propagation, how it happens with the RNN architecture. So, so what do we infer from these pictures? That's a foundation question. So, when we look at each of the pictures, as a human, we are
எல்லாரும் agree பண்ணாலும்
am I audible now?
yes, Shiva, you are audible.
Okay, thank you. It was, I guess it was muted when recording has begun. Should I continue from the first?
Yes, Shiva, just share your slide also because it's also not seen. Please
Yeah,
continue.
I just came out
Okay.
of, yes, I'll just redo it.
Okay.
Is it now visible to all of you and am I audible? I guess.
It's audible, but the screen is not visible.
Okay, let me share again. Yeah, things are out.
Yes, now the screen is visible. You can continue.
Yes. Yeah, okay, thank you, Saranya.
Yeah,
And sorry, participants, let me begin again. Okay. So, the agenda here is to discuss the forward propagation. I wish to begin from a few foundational points to discuss and go further with RNA. So, what do we infer from each of these pictures? Being a human, as we have learned so far from our childhood, we are able to classify or tell or describe what each image is or what each object is. So, because we have intelligence that is gained from our childhood and we are able to classify it, and we call such knowledge as the human intelligence or normal intelligence. And when we wanted the same knowledge to be inferred from a computer or a machine, we need to train the machine as like us right from the beginning, and it takes some time to train the machine. And such a knowledge is actually called as artificial intelligence. And that artificial intelligence is now becoming more and prevalent in nowadays, and that is why the model AI models are becoming more prevalent nowadays. And that is the agenda that we have gathered today also. So that is what I wanted to differentiate as the very first point. This is normal human intelligence, and when we wanted the same, we call it artificial intelligence. And the second concern was to discuss what a Google does and what ChatGPT does. I wanted to compare each of these entities or models. As we know, we have been using Google so far in our times, and now we started using ChatGPT nowadays in the couple of years back. So, what Google does is in the search, whenever the search keyword is given, it tries to fetch as much as details as possible based on the webs available or other details available online based on the page rank. And we further figure out what is actually wanted for us, and we need to search and filter out what is wanted for us. And alternatively, ChatGPT is a model that has come viral nowadays, and we've started using even now the DeepSeek has come. Could you describe what a ChatGPT does when compared to Google? Okay, let me comment on. Google searches and displays the results that we wanted, while alternatively ChatGPT generates the contents. That is the underlying difference among the two models. ChatGPT never fetches and displays as such; it generates the contents newly, and that is why the uh, most important topic that is prevailing in the world nowadays called Gen AI is becoming more. And that is what I wanted to comment on before we enter into RNN. So ChatGPT is a kind of generative AI model where it generates content as a fresh. Okay. So generative AI, it is actually refers to the category of AI models which actually generates new content. It not only generates text, it can also generate images, audio, and any other type of data which could resemble human content, as like a human generates. If the generative AI is intended for generating text, we call them LLMs, large language models, because it's mostly related to NLP and human languages, large language models. And if it is intended for images and audio, we have some other models coming up, and it is LLMs. So LLMs play a very vital role in the context of ChatGPT because it is highly textual context, human language context. So this is what this you know very well. I need not explain much. AI is the broader field. ML and DL and generative AI are the subfields of AI, which is coming up faster in the world. And generative AI, as I described, it is a model to generate text or image or whatsoever that that could resemble human content. So to conclude, what is this and to jump on RNN, this is the comparison. ML or DL and generative AI to compare. When we compare these two, what ML, DL does and what generative AI does. So ML or DL are the systems actually for prediction, classification, and clustering. Those are the purposes. And alternatively, generative AI is a system is actually to generate. So that is the broader sense that we have. And our RNN and their future versions and advanced versions are concerned with the orange color called Gen AI and in the context of generating contents. So that is why Gen AI is the superior model that actually evolved from the RNN architecture and from the ANN architecture. So here is the quick evolution I like to convey, which I have gathered from a few literature papers and I have articulated with this diagram. So neural networks are not new. They have come early in 1980s and 1990s, and it started long back. And deep neural networks came, and followed by the recurrent neural networks started booming in the 1990s later, and they are extended to two more models like LSTM and GRU, and sequence-to-sequence models, attention mechanisms, transfer models, and pre-trained language models and large language models. This is how neural network has actually began to grow, and now we have the LLMs that are coming up. So here is the breakthrough that you can see from the one, two, three, four, five, sixth box. Sixth box called attention mechanism is the breakthrough that happened from neural networks, and then attention mechanism has now gone to LLMs. And what I wanted to convey here was LLMs underlying principle that has evolved actually from neural networks and RNNs, which help us to predict sequences. Okay, here is the quick comparison of why should we use RNNs over regular neural networks called convolutional neural networks. Am I audible and is the screen visible as usual, Saranya?
Yes, sir, you are audible and screen is also visible.
Okay, if it is somewhere disturbed, please let me know because I'm only looking at the presentation. Okay, thank you.
Sure, sir.
And it is CNN. CNN is actually intended for image processing. That is the first underlying difference. While RNN are actually intended for sequential data, time series, text, and speech. So, and what is the architecture that goes behind is CNN uses the convolutional layers, while RNN use recurrent layers, which loops over itself. That is what we're gonna see it in the architecture and the forward propagation. And the dependency of the data is with the pixels because CNN works on the images. Because and while in this RNN, it is based on the temporal dependency and what is the relation between the data in the timestamp 1 and in the timestamp 2. It is depending on the time in the RNN and it depends on the pixels in the neural network. And memory requirement, when we consider it is lower in the CNN, and RNN has an explicit memory, and that is why there is an additional point that is discussed as memory requirement. It has higher memory requirement when compared to that of CNNs because we need to store the past information, and it goes to LLM in the next step and GRU in the further models. It goes, and the training speed is faster in CNN because parallelism happens. But in the case of sequence, we cannot have parallelism, so the training is little slower. And RNN is explicitly for long-term dependencies. But however, despite RNN is intended for sequences, it cannot predict or find out the correlations in the very long sequences and the very long text that we have. But we need to we have obviously the solutions with us with LSTM and GRE. We can go, but long-term dependencies can be captured a little. And here is the most underlying difference between the CNN and the RNN, where the input shape is highly fixed in the CNNs. The number of input neurons and the output neurons are fixed in a neural network, and if you wanted to modify, you need to modify the architecture, and that is of fixed size. But in the case of RNN, because the input is a sequence and it is time series data or text, we cannot predict how much the length of the text is. So it is of variable length. That is the second underlying principle I wanted to highlight when it is other than the first point I have conveyed. So, so this is what. But let us come to the last point because they are highly theoretical. But still, limitation of CNN. Obviously, they cannot go for the sequence or they can't understand the sequential information, but on the other case, RNN has the limitation of learning or training the very longest sequences, because remembering the very longest information is not possible with that of RNNs. We have to go with dedicated memory cells. Okay, so these are the limitations that we have compiled into why should we go for RNNs when to compare to that of ANNs. So fixed neurons are one problem, and the heavy computation that goes behind the propagation, because that is upon hard coding and other stuff, because we need to convert each of the word into a vector or embedding or whatever models that we wanted to convert it into. And the parameters are usually shared in CNNs. In the case of weights, they are shared between the input layers, but here it is not so. And also, the sequence in which the input is fed is important, because RNNs are actually intended to understand or fetch the pattern in the sequence. So, the changing the order of the sequence would probably affect the result. Okay, so that is why RNNs is the foundation question, and the slide gives you two straightforward answers. So to make predictions on the sequential time series data is the one and mostly agenda. If you have any specific problem related to this, we have to go with the RNNs when compared to any other neural network models. And as I said, the two answers on the slide are sequential data and of the variable length. These are the objectives that we should, why we should prefer RNNs. Yes. So to define what is an RNN, despite you have learned, let me comment on with crisp words. It is a kind of ANN which uses a looped architecture to process sequential data. We can represent RNN with a single diagram itself, single single box or layer of architecture itself. When we expand it, it is actually intended that, or we can say that it is a looped architecture. When we expand the single box, we try to understand the hidden neurons and hidden hidden layers that processes the sequential data across each time step. So, as we said, if RNN has to remember the sequence and its pattern, it has to remember the past information. So, in order to remember the past information, it receives the output from the past loop and gets as input for the current loop and predicts the output for the next loop. And this is how each step goes, because it is a loop architecture. So hence, it is intended for sequence and text time series data. The applications are going widely: speech recognition, NLP, time series analysis, etc., etc., etc. Okay, and these are the quite what to say, quite few examples where RNNs could be applied or RNNs are widely used. And that is why I illustrated in the very few initial slides that RNN forms the foundation for the ChatGPT or LLMs that generate contents, textual contents, because it is LLM, large language model, because it is intended for natural language processing kind of tasks, human language tasks. So, what is autocomplete? Uh, in the Gmails, we nowadays see that if we wanted to type some content, the Gmail automatically gives a subsequent set of contents. That is actually the prediction of the next word, where RNN plays a vital role. So if I'm typing not interested at, probably the Gmail would type automatically or suggest me this time, the word this time in the next one probable application. And we can also use RNNs in the case of translations, where the sequence is important, where it is also involving variable length text. So these are the applications where we apply the concepts of RNNs to translate contents. Because how are you is a sequence which could be different in length, which could be different in grammar, which has sequential meaning. How are you? If you change the words in this order, it will be meaningless in the case of translation. The translation will be meaningless. And that is the difference where we use RNNs. And NER is yet another application where RNNs could be applied. It's called named entity recognition. If you are given a sequence and or called a sentence or a paragraph, it would classify or it would differentiate the name entities or nouns available names available in the context or in the text. It is a named entity recognition where the sequence plays a vital role and the length is variable. And also, mainly it could also be applied in the sentiment analysis where the output could be based on the text that we have given, whether it is a sad or angry or happy or neutral. In the way of such classification, RNNs can also be used because RNN learns the pattern among the sequential data and predicts what it could be. And each of these applications have different variety or different architecture of RNN, depending on the input and depending on the output, which we will see in the later slides of the session, that how autocomplete or word prediction happens, and what is the architecture that is required for the translation, what is the architecture required for the NER, and so on, sentiment analysis, and so on. Each of these applications require different forms of RNN that we would see in the subsequent slides. And all these are actually called sequence modeling problems, and that is why RNN could be well applied. Yes, here is the RNN architecture that you could appreciate looking at it. So I have mentioned wherever I have taken the inferences or pictures or contents, I have mentioned at the bottom where I have actually taken from. And based on these pictures and articulations, I have made my own illustration in the later slides for the demonstration. And for the pictures, I have referenced where I have sourced from. Okay. And here is the actual architecture of RNN, where the input called X and the output expected was L, is L, actually L, and it goes inside a hidden layer called L, which loops over itself along with the weights U and W. V is the output of the previous hidden state output is fed again as the input to the next hidden layers processing input, and it goes as usual. And that is what I said earlier, that RNN architecture could be explained or demonstrated with a single box, and this is the single box which is on the left side. Input, output, and looping over, like a foundational finite automata diagram, a self-loop kind. So it is a kind, yeah, it's a kind of self-loop where it hidden layer moves or works towards itself, which means the previous output is fed into the current processing's input at time steps. So when it is unfold, you could see from the figure, the middle portion is xt and the previous input is xt minus 1, and the next input is xt plus 1. This is the sequence in which the input comes. So it is time t minus 1, it is time t, it is time t plus 1. So this is the sequence in which the
Sir,
data comes.
excuse me, sir.
Yeah,
Uh,
please.
Sir, actually, I want to clarify one thing. What I think is in RNN there is a memory associated which takes the previous output as the input. Is it
Yes.
true or
Yes, it is true. RNN takes previous output as the current input, which I will be explaining. Yes, it is obvious. As it is the unfold diagram explains you, xt minus 1 is the is current input multiplied by the weight called u, and ht minus 1 is the current hidden layer. It produces some output, and that output called V in the middle portion over here will be one of the inputs for the HT.
yeah, sir? I want to ask, is any memory associated where the output is stored?
No, no, it is not explicitly the memory that is associated. It is the information that is passed from the hidden layer one to the other when it is being processed. There is an explicit memory and explicit gates available in the later architectures called LSTM, and so here it is just being passed across the different things. Maybe you could wait for the subsequent slides, and I think you would get the subsequent contents as it goes along. Yes.
Understood, sir. Thank you. Thank you.
Yeah, yeah. If even if you have a post across, I would be happy to address at the end also. Definitely. Yes. And here is what it's going further down. So when it is xt1, xt, and xt plus 1. The content is when the last box contain xt plus 1 is wanted to predict some output lt plus 1. This lt plus 1 depends on the previous output called v that is coming out of xt and based on ht. So this h is actually expanded or iterates over ht minus 1, ht plus 1 is what actually looping that happens. Ah, this is the foundational difference among the two, except for the loop that happens in the recurrent neural networks and in the feed-forward neural networks. That's what I explained. So, as was discussing, so the input layer, these are the layers available in RNN architecture. So, what is the role and what is its structure and how is it connected to the subsequent layers or how is it being transformed? Input layer receives the input sequence one time step at a time, and each input at time t is represented as a feature, xt. So, input layer receives the input and it processes one input at a time, and it passes to the hidden layer along with the hidden state from the previous time step. This is what an input layer usually does. While the hidden layer is the core of the RNN architecture that maintains the memory of the previous inputs through a hidden state. Uh, this is what I think she was trying to ask. One of the participants was trying to ask. So it is the architecture where it maintains the hidden state. So, and in the hidden layer, probably these two are the activation functions that are quite naturally used, TANH and ReLU. And in the output layer, softmax is preferred depending on the classification problem that is being chosen. So, and a hidden layer captures the temporal dependencies across the time steps because there is a sequence and it output depends on the previous inputs computation as well. So the temporal difference is temporal connection is also maintained. So output layer is intended to generate the output from the final output of the all the looping that has happened and converts the hidden state into meaningful prediction. That is the task of the output layer. So this is what happens and where the hidden layer plays the vital role in the RNS core architecture. Mhm. So when input layer processes the data and when it is feeding to the RNN architecture or hidden layer, it has to process and it should give it in the form of numbers because the computations are highly mathematical. So different forms of encoding could happen with input layers. So because we could use text because we highly involve natural language processing tasks. So the strings must be converted or the text must be converted into the numbers. So we could use different forms of encoding techniques for the input or sequential data. So these are the famous or popular encoding techniques. One-hot encoding, word embeddings, and normalization. So these could be different models that we could use, and most of the models use the first two, one-hot encoding and word embeddings. So these are highly used, but vectorization becomes huge when we go with these models. But anyhow, the computations will happen behind the screens. Whatever we study on these theoretical aspects would be written in a single line or would be highly hidden in the code. We would see just the code that is happening and output that is being coming up. But whatever we discuss on these slides are highly mathematical calculations and theoreticals that actually happens behind the code of the Python or whatever language that we implemented. Yes. So that's what to answer on the line one. We have an internal state, hidden state in the RNN architecture, which acts as a memory through a feedback loop in the cell. It is a cell. But one point here is, unlike the traditional architectures like CNN and ANN, RNN maintains or standardizes the activation functions, weights, and biases across the different layers, which means through until the forward propagation is over, it doesn't change the bias or it doesn't change the weights that are assigned from the initial step. once the complete iteration or once the complete loop is over, and when the back propagation processes, the weights are updated in the BPTT. So back propagation process. Until then, the weights are kept common and the activation functions are kept common until the training of the one sample is at least is over. So, and one more, and at each time step, RNN processes each unit with a fixed activation function. That is what the second point clearly states. As we saw from the architecture in the previous slide, look at the point 3. That is what to be highlighted. It forms a single hidden layer that loops over itself instead of depicting multiple hidden layers. We have distinct hidden layers. We don't have. And as we have been discussing in the architecture, each cell has two inputs. One is the past output and the present input. Even though we call it input, one of the inputs is the output of the previous iteration or previous loop. And what we call as the present is the present input in the sequence. I think you could understand from this illustration stores from one of the websites. So input B and constant, and it produces applies an activation function and it produces the output called Y. And this is what the single layer illustration, and when it is unfold, we continue to do the same. First one at timestamp 2, timestamp 3, timestamp 4, timestamp 5. It is how it goes when it expanded. And each of these is called as a looping, and previous
Sir, you are muted. You are muted, sir.
yes, thank you. I think audible now. From when I have been cut?
Yes, sir, you are audible. Yes,
Audible.
yes, from
Should I?
after this slide, sir, you were unaudible.
Okay, fine. Thank you for the notification. And this is how the architecture goes, a GIF kind of thing to illustrate. And we have to process one input slice at a time. That is what RNN is actually doing over each iteration or each loop. And once after each loop is over, we calculate the error or the gap that is being done. And we, at the end of the forward propagation, we also find out the loss, and that loss is explained in the overall final step here around. Okay, and this is what these are the different activation functions which you could use in the RNN architecture. Various things are given. A few things are used in the hidden layers, and a few of the things are hidden state output. Used sigmoid TANH. These are used widely in the sorry. TANH is used widely in the hidden layer state, while sigmoid softmax are widely used in the output layers, depending on the classification task. So as I told, C sigmoid is used for the classification task as applied in the last thing, and softmax is for the multi-class classification problems. ReLU and TANH and ELU are could be probably used in the hidden states when the loop iteration happens. So this is a VAR and visualized. So here is the picture I have sourced from one of the um, videos available online because I found this illustration going good. So remember the word, remember the sentence or a sequence. Dawal loves baby Yoda, and we call this problem the name entity recognition problem. What Dawal means, what love means, what baby, and what Yoda means. What are the nouns available in the sentence to classify this? We use name entity recognition problem, and we apply RNNs here to predict what is it. So the wall is the first word which is passed in the first time, and it is represented in the one hot code form or in embedded form, and that is what represented in zeros and ones. Those are converted into vectors, and it is at time 1. And this is in the first iteration or in the first loop. It is expected to produce some output called y the word. All are highly numerical. And coming to the second word called loves, louse is also represented in the form of some vector, in the form of one card encoding or some other embedding technique discussed in the earlier slide. And it also takes one more input called y the wall, which is the previous output. These two are the current inputs to the current iteration, and it must produce y louse. And it continues to the third word baby, and it also continues to the fourth word Yoda. And the end of Yoda after processing, because this input sample, one input sample, we have only one input sample called this sentence with 4 timestamps because we have 4 words. And once the fourth word is completed, the model is about to predict 4 is to 4 because it is multi word, multi input, multi output. That is what I said. Depending on the context of the problem, the architecture of the RNN has to be decided. That we will see in the end of the slide. I have mentioned what type of architectures are available. Okay, so this is how it continues, and this is the expanded diagram of what the statement of this corresponding statement. So the one A0 are the current inputs, and A1 is the predicted output in the first iteration. Louse is the second word at the timestamp 2, and it continues so long. This is the expanded diagram of each of the diagram on the left. Continuing the same, this previous diagram, what is on the right side is represented in this form. This is another representation because in regular architectures, the input is usually specified at the bottom of the layer. So here comes the input Dava, Louse, Baby, Yoda. Each of these words are passed to the hidden layer at each of the time step once each iteration is over. And each of these iterations would produce output called A1, A2, A4, etc. 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 This is all. And remember what happens, as we told, each of these iterations would require two inputs, as we saw in the earlier slides, the past output and the present input. And what happens to the first layer, first word that is called the wall? The wall has no previous output, so we randomly initialize a weight or randomly initialize the output through some forms, and that is the logic, and there are different methods to initialize the same also. And this is called weight initialization in the architecture, and this A0 is random. And this is the simplified architecture, one line or one box architecture of the entire RNN, which is on the left. So this is actually the most general form of RNN. This is all.
Sir,
Yes, please.
sir, in your previous example, uh, sir, please go to the previous slide. Is this. So first input will be double. Then second input will be
Love.
double plus loves.
Yes. Dawal's
Then
information. Yeah, I have got it. Dawal's information or
double
the
plus loves. Yes, sir.
yes. A2
And
will
for in
contain
the
Dawal
third,
plus louse. Baby
uh,
will
i-
contain yeah, go
double
ahead, go
plus
ahead.
loves plus baby.
Baby.
And the last will be double plus loves plus baby plus
Baby plus
Yoda.
Yoda.
Yes,
And
sir.
that is the point where RNNs are used because the sequence information has to be maintained from the previous layer to the current layer. And that is why
Yes, sir.
Dawal is remembered until Yoda comes.
Yes, sir. Yes, sir.
Yeah, sorry. And this is yet another application where language translation happens. So how are you is being transformed, translated. This is how encoder decoder architecture works in the Google translation. So here the sequence is also required, and the decoder works only after processing all the inputs. Only after A4 is obtained, the decoder will start continue to produce the translated content. In the case of this previous example, as I told, it is actually intended for named entity recognition, where the number of input varies and the output is also varying. We have to specify in the NEP problem how many number of nouns are there and what are the nouns are there in the given statement or in the given training sample. In this example, it is not the same. You translate one language to another language where the number of inputs and the number of outputs would vary. Here also it is the same, but here the architecture translates from one language to another. The sequence information has to be maintained. This is another architecture, another application of the RNA. I have been explaining so far the same, but it is another illustration of the same. But however, at the time two, the second influence at time two, the first input is processed and it is fed to the time two. The second input influences the output based on the time one, as she was explaining. The wall plus louse plus that kind. And this is the training that happens. This is the overall picture. Here is what the actual agenda lies. So it is a complete cycle going from the input x1, x2, x3, x4, and the initial thing is the forward pass, which is indicated in the orange color at the top right. And once after the loss is being calculated, we have to come to the bottom and we go backwards, and which is called the backward pass. And when we go from this left orange color to the right orange color on the top, the weights are not updated, they are kept as such. And while coming back after calculating the loss, the weights are being updated and modified. That is what specified, adjust all the weights to reduce the loss. So the what happens in the training RNN is there are four foundational steps. Go with the forward pass, calculate the loss in the second step, and based on the loss, you go backward, update the weights, and do again. So our underlying problem is going with the top box, the forward propagation. Okay, so this is what how the input is being to the forward and how is the loss calculated. This is highly this box is mathematical, which is what I'm explaining here. So let us take an example here. I have made from the textbooks and various illustrations available online, and I tried to simplify as possible as it. And different websites, different textbooks, different YouTube teachers demonstrate in different ways. The formulas would be different and notations would be different, but the concept I deliberate here is quite the same. So I wanted to simplify the notations because it is highly mathematical, understand what goes behind. So let us consider only one training sample, which is called as X. Assume X is one of the sequences containing four parts, as like Dawal, Loves, Baby Yoda. So it is one. We took only one training sample. If you have multiple sentences as like a paragraph, you have more samples to have, because as we take only one sentence, I say it is one training sample. Okay, so that one training sample itself contains four inputs, and the output expected is y dash. It is expected to be 1 or 0, because the problem that we take up here is the sentiment analysis. Okay, and actual output of the input is y, and the predicted output, which I mentioned on the slide, is y dash. Okay, and the loss is calculated at the end of the forward propagation with the difference of the predicted output and the actual output. The formula is quite clear: y dash minus y. And the input layer weight that I have considered here is w. Layer to layer, when it is being communicated from one iteration to the other iteration, is w1, and output layer's weight is now represented to be w2. And the number of timestamps or time steps or the number of loops that the model takes up is 4, because we have 4 split inputs. Okay, and here is what happens in the RNA. So this is timestamp 1. We are currently at time t1, and the current input to be considered is x1, and the current weight of the model is w, because we go in the forward direction. And this is what, remember these rose color boxes being the bottom of the architecture, where the input is fed and it is going to the hidden layer at the middle of the box, and at the top we get the output, as I explained in the architecture of the previous slides. Okay, and x1 is one of the inputs at the current time, and w is the weight that is going along with the w. sorry, input x1. Okay, and this is how the output 1 is calculated in the first hidden layer or first loop when it happens. So there is some hidden state as we have been discussing, and that hidden state applies some function called f. That function could be tanh, relu, or whatever. So I mentioned in the earlier slide. That function is being applied on the product of x1 along with the weight. This is the first output. And now remember, this O1 called output 1 is the input, is one of the inputs for the time step 2. Okay. At time 2, we are in a position to process the second string called x2, and there will be no change in the weight because w will be the same w, because during the forward propagation no weight change happens. And how the output 2 is being computed? Output 2 depends on two parameters: output of the previous loop and the current input. Output of the previous loop is O1, input of the current step is x2. So remember, x2 is multiplied by the current weight w added with the output earlier and the weight 1. Weight, understand the difference here. W is different weight and w1 is another different weight. In the earlier slide, I represented three different weights are being considered. One is the input weight, another one is the output layers weight called W2, and one more weight called W1 that moves along with the iterations, which is called W1. Okay. And when we move the next iteration, it is called the time step 3, and the current input to be considered is x is equal to 3. So x equal to x3, that is the current input being considered, and there will be no change in the weight during the forward propagation. Output 3 is now calculated based on the current input x3 multiplied by the current weight w, along with the added values of the product of output 2 and the weight 1. I guess you catch it. And when continuing, it is the same. This is how it is being computed. This is the mathematical computation that goes behind each of the iterations and each of the input sequence that is being maintained. This is how it is being transformed. And once the output 4 is obtained, once the input sequence is over, this output 4 goes to another activation function to get it classified or to get it predicted. So, and that is called y dash. Again, this f, what is mentioned on the last rose color box is quite different. It could be softmax or as a sigmoid, depending on the application that we have taken up. And the output 4 is multiplied by the new one of the new weights called W2. Remember, in this particular slide, we have used three different weights: W, W1, and W2. W works along with each input sequence. W1 goes along with the iterations. W2 works only on the output layer. And remember, the functions across the first O1, O2, O3, O4 is different, and the F function applied on the Y dash is different. Okay. And across all the steps, the biases are added along with these outputs that are being calculated, which will be represented as plus B plus B plus C in the different notations, but I have skipped it representing. And each of these outputs are associated with the biases being added and passed on to the layers.
Excuse me, sir, one question.
Yes, madam.
Sorry. The weights which you are fixing, W, W1, W2, is it a real number or how we are fixing that?
Yes, madam. Ma'am, it is depending on the random initialization. The first W, which is going along with the input, is random, and we have different methods of it. And and depending on the one padding that we have taken up and the input sequence that we have. And in the case of strings, if we have taken four. One second, madam. ஆனா ஒரு half an hour நான் 7 மணிக்கு முடிச்சிருவேன். I lock it. Sorry, 40 seconds. I'll hold it for a sorry. I'm sorry for the interruption. Am I audible and the current screen visible?
Yes, sir.
All right, thank you so much. And this is how, and there was a continuation going, and it is a random initialization, and that is why the number of iterations go, and the number of epochs that is going. So we initialize at the random zero in the initial weights called W. That's what I'll be explaining now. Holding on, and the biases are added. And once this complete O1 to O4 and Y dash is over, we call this an epoch. And if you wanted to train the same over as many number of times as possible as your model requires, when it converges or it produces the expected result, you have to continue until then. So this we call one complete epoch. Uh, we train the model over 100 epochs or 50 epochs depending on the model's architecture. That's what I like to comment on the next slide. I think madam's answer would be addressed here. As I have been telling, each of the output uh, in the current step requires previous output, and what happens actually at the time t1. This very first O1 does not have any previous input being associated, and that is what randomly being initialized here. I am commenting on here. That is called a T1, and current time T1. The current input sequence is X1, and the weight is currently W across the input, and it has no previous output being associated. So this is the first thing that we have discussed in the earlier slide. In order to have some output added to the first layer itself, so initializing the first output to have being this, it is being initialized to 0, and it is 0 padded. That's what I have been telling. And the padding means if we have as many number of input sequences in our architecture or in our training sample, we have taken only one training sample in our example. If the training sample contains multiple sentences, and each of these sentences must be converted into the same length in order to process the input in a proper manner, and those missing slots are filled with 0, that is 0 being padded. So output, the first output is expected to be initialized to 0 and 0 padded and being multiplied with the current this one, so that the formula could be generalized in this way. O1 output 1 is actually depending on current input x1 W along with previous output O0 multiplied with the hidden layer weight called W1. This is the foundational architecture that actually goes in the forward propagation. Ah, that's what F is in the Tanish and Relu, and here in the case of uh, output layer, we go with the sigmoid or for binary classifications and softmax for the multi-class classification problems. Ah, finally the loss. Loss is calculated between the differences of the current and the previous, expect actual output and the predicted output. So the total loss is calculated being the sum of the losses of the each step. That is what being described as the bias. So L is the that is being described in the earlier slides itself. L is the loss and Y is the actual output and Y dash is the predicted output. The difference being calculated, and this is what propagated through back to the input layer again, being the weights updated, called the backward propagation. So this is what happens in the forward propagation architecture of an RNN. While what is the need for back propagation are the highlighted pink colors. So we need to update the weights and learn dependencies across the different time steps, and we need to compute the loss and back propagate to retrain the model with to predict the or to reduce the loss. So that is what in the fourth point is being specified. Minimize the loss by adjusting the network parameters, and it is essential for long-term dependencies. Why should we go backtrack to understand it? And to avoid the vanishing or these gradient problems, we need to go with the LSTM and GRU kind of things. And this back propagation helps us to improve the model's accuracy. I'll before this, let me comment on this. These are the common architectures. I'll come back to these limitations later. These are the common architectures of RNN. The evolution of RNNs that has happened, as I was describing in the earlier slides. LSTM, GRU, and attention networks. Attention networks are the foundation for the current generative AI models, and that has evolving from the RNNs. LSTM has memory, GRU has even additional memory, but the gates are being combined to reduce the computations, and that is GRU, gate and recurrent units. And these are the common architectures again, represented in the pictorial form: RNN, LSTM, and GRU. And these are the various forms which I was interested to communicate with you. RNN architecture could be applied with different forms of these, depending on the different context that we wish to apply. So in the first one, it is a one-to-one RNN architecture. We have one input and the model is expected to produce one output. It is a traditional neural network architecture. In the case of second, it is one-to-many, where there is one input and we are generating multiple outputs based on one current input. One such example is the music generation. That's what given here. And in the form of third, many to one, we have multiple uh, inputs that is being given, and we expect one output to produce out of the RN architecture. And this is what the example we saw, the sentiment analysis in the X1, X2, X3, X4 we have been discussing. And in the many to many architecture, uh, inputs are many, outputs are also multiple, many to many correspondence, where it could be used for named entity recognition, also for that machine translation. But there is one underlying difference. The output is produced in the case of machine translation. The translation happens in two phases: learning and then the translation. That is what being split into that's what being split into encoder and decoder architecture. The inputs are encoded, and decoder generates the output, or machine translation happens once the learning has happened. And in this many to many of the last architecture called machine translation, this first green and blue colors, the sequence has to be maintained and learned over the time steps, and the correlation among or sequence information among this is crucial and has to be maintained to produce what is on the return other side in the decoder part, because the translation requires the meaning of the sentence to be maintained. It cannot predict one word for one word. It has to learn the sequence and the meaning of the sentence and then produce the meaningful translation out of it. And this is how RNNs work in the forward direction, and RNNs could be used for text generation. or any kind of other applications related or specified on this respective slide, different applications of RNN. And that's it for the day. I have made contents on this, and I thank you. And Professor Saranya, am I audible?
Yes, sir, you are audible.
Hello, sir. Hello.
Yes, sir, you are audible, sir.
Professor,
Hello,
we can
sir.
see some question asked in chat box. Kindly answer those
One
questions.
second, 1 second, sir. 1 second. I have been.
Thank you, thank you, thank you.
Yes, yes, it's been. Okay. I'm seeing couple of questions here. Let me try addressing. Good evening. Your statement having references, Professor, kindly share it. Yes, definitely. And we put it on this one slide. Slide 35. Can we use AI to produce various forms of RNA? I couldn't get it. Slide 35. Can we use AI to produce various forms of RNA? Could you explain what is the question? AI to produce various forms of RNA.
Yeah, yeah. In slide 35, you shown a lot of RNN methods.
Yes,
Professor.
yes.
If it is use AI to learn that one, and we produce lot of various method is possible.
You mean to say whether can we generate models through use through any of the generative models you asked, Professor?
Yes, 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 Professor.
Yes, yes, definitely, definitely. Yeah, now generative AI is generating everything, and we are able to produce anything and be specific in the context that we wanted to use, and depending on that, we can develop models out of it.
Okay, Professor. Is there any references regarding AI using RNN like that?
Is there any
Different
reference?
model current references is available, Professor.
For you to refer or learn, or what do you like to convey, Professor? What do you like to?
I need to learn that those things. That's why I'm asking.
Yeah, yeah. I'll let you know few couple of videos available and sites available. I'll share it across the coordinator, Professor Dr. Saranya. I'll ensure that it reaches you. Otherwise, what I'll do is I'll include a reference slide at the end of my presentation, and I'll share it across with Professor, which will be easy to access.
Okay, Professor. Thank you.
Definitely, definitely. Because I have came across several slides and several videos for the better demonstration and illustration, and that is even I have come across a few slides and books which were quite useful in learning and going through. I'll definitely share it with you because using someone else's content is not that good, and that is why I have referred wherever I have taken examples out of.
If using RNN and we can use ANN, Professor, it is possible.
Yes,
I'm
sir.
working on
ANN,
ANN.
yes, sir. ANN model is the what to say. If you are ANNs are suitable for particular applications, and RNN is recurrent is suitable for as told for time series data. If your application involves such, you can go with this.
Okay, Professor. Thank you. Thank you, Professor.
How the number of zeros padding are determined and in the forward method. Depend how the number of zeros for the padding are determined depending on the maximum length of the training sample available in the training set. We have taken exactly one training sample in our example. If the training sample contains 5 sentences for an example, or if out of the 5 sentences in the training sample, if one sentence contains the length called 10, which is maximum among the other training samples, it would be uh, one more than the 10, which means one more than the maximum length of the training sample. You get it? Suppose if you have 5 statements and one of the statements is having the maximum length called 10, around 11 padding will be utilized in the initialization. That is how the padding zeros is being computed. That is what I said. The padding when before even training starts, the vectorization has to be uniform. It is being frozen before the training starts. Okay. I mean it's time series Wi-Fi. Need a good architecture for Wi-Fi sensing. Need a good architecture for Wi-Fi sensing. Okay. Could you tell your application so that I can comment on? Somebody requested for Wi-Fi.
Sir, am I audible?
Yes, yeah, you are.
Yeah. Basically, I'm getting some signal from access point.
Mm-hmm.
So there I'm observing the power variations.
Observing power.
Variations at the physical layer level.
Okay.
And that pattern is similar to our speech kind of thing.
Okay.
And I want to use it for activity detection.
Ah, I mean, I think it is quite related to anomaly.
No, not normally, even standing, sitting, posture, falling, gestures.
Okay. For an example, at respective time T1, some signal happens, and later after the time step 10, some other things happen. You wanted to differentiate what happened at T1 and T10, is it not?
No, sir. Actually, when event happens, it has a time span.
Ah.
That means when you sit now, like in between, multiple packets may be communicated, and that gives the power variation.
The power variation happens across the times, and you get the differences. What inference you can make out of it is under what circumstances the power variation happens. Is that your concern?
That it is something like you said, when you train our speech and all, for a particular sound, you have one pattern of variation. Another
Yeah,
sound,
yeah.
you have another variation. Similarly, when you do an activity in a room kind of thing, when you see the signal, like when there is communication between two entities, if you are capturing the signal, probably the kind of activity in the room will be able to capture the variation.
Yes.
So it is a time series. It is a time series. Already we are working with LSTM. Already I'm using LSTM, but like accuracy is only 94%.
94, even that is. You need to improve even more beyond it.
Yes, sir. Yes, sir. In literature already they are there.
It's 94. Even what we have done was we actually when we solved our autonomous vehicle problem, as in the introduction people said, we are working on autonomous vehicles. It's quite the same. I implemented using the LSTM architecture for my anomaly, I mean the classification of anomalies. in the later, even one of the sessions when our students presented the same problem, we were suggested to use GRU. Hello?
Sir, how about its memory requirements when I run on GPUs and all? Will I be able to run or?
GRU.
Yes, sir.
Yeah.
Like, what about its memory requirements? Because GRU uses some memory elements.
Mm.
So in its architecture, where I need to have more
Computational resource.
yeah, computational resource. So my laptop, which is having the GPU, will it suffice?
If your laptop is having like additional graphic card like Nvidia and also when compared to the other normal laptops, you could probably run, and that too if the heat is not being generated much. Otherwise, you need dedicated things going around. Even Colab cannot run more beyond 12 GBs.
That's fine, sir. Apart from these two, is there any like a workaround or any alternative to this?
To
Apart from
implement, you
these two?
ask? Are
Yes,
you
yes,
asking
sir.
for the implementation in the
LSTM and GRU, like any other techniques, any other algorithm?
in that case, I need to refer and tell you what would be the better architecture for your model. Let me have a comment and get back to you on this through professor, or share across this mail. Maybe I'll share here my mail ID here. You can definitely ping me. I'll get you that one.
Yeah,
Definitely.
please, sir. Thank you. Please, sir.
Definitely. And your good name is
Ravi Kumar.
Ravi Kumar.
Yeah.
How
Thank you.
effective is the RNN when the data size is small? That's what I think Ravi Kumar sir. When the data size is small, the dependencies can be learned better. When the data dependency is more and the input sequence is long, we obviously require memory to go ahead. And I'll share my presentation. Okay. How can we use GRU for ECG analysis? I think it's a recent question. And the GRU was one question. And did I miss any previous questions? So through initial. Oh, கொஞ்சம் பேர் வரல. I address these questions. Sure. One professor asked about attention mechanism, which I am a learner stage. I cannot comment even without completely knowing about attention mechanisms. I seek attention here to you. I'll explain once after complete understanding. I'm sorry on it. And I think I addressed the questions.
Sir, can you share some open source links if you come across for GRU?
Open source?
For GRU implementation.
Open source links. Implementation.
For GRU. Yeah.
Yes. I'll share across. Even my students have implemented, but it is on the different software. We have used some Carla model for the simulation. But anyhow, I'll let you know how can we leverage GRU with some other models. Yes. We have a lab here. We have NVIDIA lab going around here. I'll fetch how they do the things around here. I just recently landed with this university. I'll find out what happens with the NVIDIA lab and get back to you on this.
Any possibility of summer internship to students?
Here in the campus?
Offline or online, whatever it is, during the summer?
Are you asking at our institute, professor?
Yes, sir.
Yeah, I saw one of the students, BSc student doing internship here. He utilizes the lab facility available here. I think he stays here for a period of 3 to 4 months and he's taking results out of it. He's doing. Let me identify the potential of doing it. I'll definitely figure out this option also because I'm a new joinee to the institute. Let me understand the procedures. But there are options to do. There are options to do. Uh, maybe. Uh, And here is my official mail ID, which I have posted across. Please utilize this mail ID for any clarifications and the NVIDIA lab and GRE architecture few people have asked for, and a few couple of internship few queries were being asked. Please get connected to me through this mail ID, and I'll possibly get back to you with the best results. Definitely, I'll do my best from here, from my end. Definitely. And please mail me in a way that what domain of internship is actually wanted, uh, or what domain and what discipline is actually wanted. Please specify. I'll also get back to you with the relevant details and the contact of the professors to communicate with. Okay, thank you so much everyone for the patience, and I think this presentation could have helped you a better. And thank you so much for the opportunity, Professor Saranya. And if you have any more further questions going around, let me know, and I'll be happy to address you through the mail and other queries. Saranya, Professor Saranya.
Thank you. Thank you for the wonderful
Thank,
session, sir.
thank you so much.
Dear participants, we could break the session for a few minutes. Kindly stay tuned for the next expert session. The session 1 attendance and feedback form will be posted in our chat box. The same link for attendance and feedback. Dear participants, kindly fill the attendance and feedback form for today's session. Kindly stay tuned for the next expert session. Dear participants, kindly stay tuned for 5 minutes. Now we have with us Mr. R. Ranjit sir and cloud engineer at Asan Technosoft, Coimbatore. Profile of the speaker. As a distinguished engineer, he holds a degree of Bachelor of Technology from Adiyaman College of Engineering. He had an experience in designing, deploying, and managing cloud solutions using Amazon Web Series as an cloud engineer. He is dedicated to staying updated with the advancement in cloud computing, DevOps, and AI driver automation, eager to apply expertise in optimizing cloud environments and delivering innovative high performance solutions. He configured and managed EC2 instances, VPCs, IAM roles, and security groups, implemented auto scaling groups and elastic load balancers for traffic distribution, managed AWS S3 buckets with lifecycle policies. He had done projects in the topics of hand gesture recognition, BMI calculator app with Kiwi, Unibind plywood website, and Hardcare with Django framework. Welcome you, sir.
Thank you. Am I audible? Hello.
Yes, sir.
Yeah, am I audible? Thank you.
Yes, sir.
Thank you. So good evening all.
Good evening, sir.
Yeah, here I'm going to take back propagation using increment using RNN algorithm. So basically we have three algorithms in AI. First algorithm which means CNN. So CNN means conventional neural network. So it is used for image classification, facial recognition, medical imagining, self-driving cars, and satellite image processing. So we are using CNN for. So this identifying classification. Image classification means, for example, I'm giving a single image to the machine, so it will recognize the grayscale image. After that, it will be given to the model which trained in the AI model. So it will recognize it is an object, or it is a hand, or it is a face, or it is a right hand or left hand, or for example. Okay. So we are going to see next facial recognition. Facial recognition, which means we are going to already we have in a real time example we have in Android and iOS, which facial recognition using unlock and etc. in iOS from FaceTime. So it is there. So now we are going to see next conventional neural network as brain tumor scanner. So brain tumor scans and MRI scans has been used by CNN algorithm. So we have another one algorithm as named as KNN. So K nearest neighbor algorithm. So this is used for best for classification and
Kindly
recommendation.
share the screen, sir.
One minute.
Dear participants, kindly wait for a few minutes.
Am I audible?
Yes, sir.
Yeah. Okay. Sorry for the inconvenience. Okay. We have seen CNN algorithm and the application which have been used in CNN. So now we are going to see KNN algorithm. So this is also a simple machine learning algorithm which finds the nearest block points and data points. For example, KNN applications are like for real-time examples, we have Netflix and Amazon. So in Netflix, how sorry, how KNN has been used means so the recommendation.
Sorry for the inconvenience, sir. Unmute to the mic. I will mute the mic, sir.
You are not audible, sir. Sir, you are not audible, sir.
Am I audible?
Yes, sir.
Yeah, thank you. So now we are going to see KNN applications, KNN algorithm using applications. So in Netflix, we are going, for example, in Flipkart and Amazon, we are going to see some. We are going to search some products like mobile phones or laptops or something else. So we are going to search. So in that Amazon website only, we are going to search the products, but it will show in a Instagram also. It will show in a Netflix. Netflix for recommendation. For example, you are going to see a K drama or something Marvel films or some kind of films you are going to see means. So it will be recommending such movies will be released means it will be recommending also. So next customer segmentation. So customer segmentation means so, for example, in Amazon, you are going to see three, four products which brought by you, and it will be recommend to another persons also in your contact. So this is customer segmentation. So spam detection means so for example in this Truecaller now spam calls is coming means it will be detected and prior information will be given to your display also. So handwriting recognition, for example, credit risk assessment, same. So RNN. Now we are going to RNN. So RNN means recurrent neural network. So this is used for sequential data. So we are going to take a time lap of a single day, which means 24 hours or a text or a speech. So for this sequential data, we are going to extract the data set. So the data set which given to the library called NumPy and another library called Pandas. So Pandas library will deal with the large number of data sets, which given to AI machine. So AI machine will be recognizing the data set, which means, for example, um, I have a data set which means 1,000 members have been ordered a food in a Zomato or a Swiggy. So what can I take? What informations can I take from your orders? I can take your address. I can take your name. I can take your method of delivery, a cash payment or card or UPI payment. Like that informations all I will be collecting and I will put in the data set. After that, the data set will be given to a AI model, which means trained model. So it will be predicting the approximately two members ordering a food means how much it will be cost. So approximately five members ordering a cost means approximately five members eating means so it will be costing like around 1,000 rupees, for example. So for example, so this is RNN algorithm using a time and text and speech. So so for example, nowadays Google Assistant will be talking in Tamil also. The Tamil which languages also you can take from Google Assistant. So for example, in most of the people don't know English language. So we are going to train a model which means in all languages. All languages means it's easy to train languages. Why? Because we have all the data sets pre-built in a predefined data sets we have. So we are going to train a model which means all languages. So next machine translations. So Google
Sorry for inconvenience. There is some technical issues, so kindly wait for a few minutes. Sorry for inconvenience. There is some technical issues on resource person side, so kindly wait for a few minutes.
Hello, am I audible?
Yes, sir. Yes, sir.
Yeah, thank you. Oh, yeah, thank you. You can change the slide RNN applications. Yeah. So we have seeing that third application called chatbots in next slide, please. AI assistants. So these chatbots are worked by. So we are going to see a lot of data sets in AI. Okay. So for example, we are going to find a plant disease in a AI chatbot. Okay. So we are going to feed a number of data sets through the data set. So in the data set, we are going to give a images like from day one to day one to we can get a fruits or we can get a vegetables or like that. For example, we are going to get no so that life cycle we are going to see in a chatbot. So we are going to train a chatbot in a life cycle of a plant. So we are going to find a just
Sir, you are not audible, sir.
Hello. Hello. Anybody listening? Hello.
Yes, ma'am.
Yeah, yes, ma'am.
Yes, madam.
Yes, sorry, sir, but we are waiting from more than 40 minutes, sir. Actually, this time is very precious, sir. We have already skipped our daily use task na, for the presentation. So please do something.
Ma'am, kindly wait for a few minutes, ma'am. There is some technical issues on resource person side, ma'am. Dear participants, wait for 10 minutes. There is some technical issues on resource person side. We will resolve it as soon as possible.
hear me? Can anyone please hear me?
Sir. Yes, sir.
Sir, can you hear me? Hello. Hello.
Yes, sir.
Hello.
Yes, sir.
Sir, can you hear me,
Am I
sir?
audible? I can hear you, sir.
Yes,
You are
yes.
audible,
Just
sir.
give me a minute. Yes, yes, you are audible. Sorry for the technical glitch which is happening now. Plus, give me just a minute. Because due to time constraint, we have 30 minutes of time. I will try to explain the concept in a very simple manner. Is the screen is visible now?
Yes, sir.
Fine. So good evening to all. And really sorry for the delay. So just without wasting the time, I would like to go for the presentation. So I would like to start from the beginning. So the today's topic is about recurrent neural networks by weight incrementation, which means the back propagation. So what is meant by neural network? Basically, everyone knows about this neural network. The concept behind this is the total number of inputs and hidden layers and the output layer. All these three are interconnected in a neural networks. For example, the output of that particular structure will depend upon the combination of the total number of inputs and the hidden layers. So the basic thing what you must know in the neural networks is the hidden layers are not at all constant. This may vary based upon the user on how many layers they are choosing and then what type of combinations they need. The first thing, inputs are getting multiplied with the number of sequences in the input layers. What will happen? The complexity of the system of this neural network is when the complexity increases, it will give more clarity and more stringent outputs where it will be the best among the generated outputs. This is the main advantage of neural network. For example, so coming for neural networks, for example, this neural network, what is the meaning for this back propagation? A normal neural network cannot store the previously generated values. So in which this normal neural network can be referred as a feed forward neural network, which means you can give the input, it will process, the output will be generated. You cannot go back and you cannot modify any input values. Now, important concept here is how the input values can be changed. So between the inputs and the hidden layers, there is the most important part which comes into the neural network is the weights, which means on updating the weights of each and every stage, the inputs can be changed so that the process will take place again and then output will be generated again. This is the process that will happen in a back propagation neural network. So for this back propagation to happen, I need a specific memory state in which it can store the previously generated values. Then only it can compare the existing value with the new value. So maybe you may be very well versed in the digital electronics concepts. For example, like sequential layers or then we can say the sequential circuit mainly consists of the past, present and the future state. So now when going for the past state, it will be taken as n plus n minus 1, current state will be n and the next state will be n plus 1. So now the concept here coming for the forward propagation, the recurrent neural process will be taken in terms of the input process will be input values will be processed. It will go for the hidden layer. It will generate first output. Now, if the user thinks that this is not the exact output or the desired output which is required, now again what will happen? This will go back to the input state again. Now a new set of input will be taken, which means the weights will be updated so that input will get changed. Now the newly generated input or the updated weights will be compared with the existing one. Then again another output will be generated. Now I will be having already generated output plus the new output. Now out of these two, which will be the best? Again, if it finds it is not the desired output, again it will go back. So for each and every hidden layer, there might be n number of weights update. It depends upon the total number of weights which we are assigning at the stage 1. For example, the first input will be connected with the first part of the hidden layer. Now here I'll be having weight as W1. Now the same first input, if it is mapped with the second part of the hidden layer, the weight will be W2. The same first input will be mapped with the nth value of the first hidden layer, that will be Wn. So now W1, W2, etc. Wn. whenever these weights are getting updated, the outputs will be getting changed subsequently. So by this complex generation of n number of inputs. So for example, to explain in a very simple way, first I have one output value which is called y1. Y, for example, x is the input, y as the output. Now I have y as the output. Now if this output is not the desired one, again I have to go and update the weight w1. Then again, if this weight w1 is updated, I can take it as w11. Now the output generated will be y11. So when the complex numbers of inputs are generated. So in maths, we know very well for one particular problem, there might be n number of solutions. Now, why we are working very stringently on this neural networks nowadays. Now, if you see, these are the very base of the neural network. So currently, I am working on many medical related applications. I am taking this neural network as one of the input for generating the best solution with the optimization algorithms. Now the concept is, if I need one input as the best one among 100 outputs, I have 100 solutions, but still one will be the best, which is very effective and which can give the highest accuracy. But we cannot say neural networks always will attain higher accuracy. When it is being integrated with any of the other optimization techniques or any other external part of the technique, then I can say this neural network will be more effective. In that case, this backpropagation neural networks will be the only useful part rather than the forward propagation. Because in forward propagation, as I said, there is no place for saving the generated values, which is previous value. So if the previous values is not there, what will happen? I will not be able to generate the new output. So only one way process is possible in the forward thing. And when coming for the recurrent neural networks, recurrent in the sense it will take part again and again. So each and every input will be processed step by step, and so for each and every time one output will be generated. So out of all the generated outputs, which is the best one? But when we were talking, it may go for n number of times, or the timing will be very long, but still when it is working, it will execute in a fraction of a second. That is the specialty of these neural networks. Now, how we are knowing that when the output generated is not the desired value? Now, for example, if you see the first point here, the RNN compares its output to the correct answer. Now, I will be defining this is the output that has to be generated. We know what is the output that has to be generated, but the RNN is not doing that. So what will I have to do? I have to go and update the weight again. Then that particular generated, the updated weight will be get processed. Then that particular output will be compared with the correct answer. So each and every output, when it is being calculated or when the weight is being updated. So be very clear, when the weight is getting updated, now we are going to calculate the last value, which tells how much percentage it is giving an error when compared to the earlier value. Because if you see the neural network outputs, it depends upon the classification. For example, if I have two different classifications in a problem statement, so the neural network outputs will be either X or Y. For example, if I define X and Y as the output, it can give only X and Y, because you are programming already based upon the inputs, the output can be either X or Y. That's for any other outputs. Now, if I calculate the error value, then only I will be able to know with the exact value which I have defined what is the generated output. Then I have to make the difference between the generated output and the original output. So now this is the second important step in the RNN. So when coming for back propagation, sorry. When coming for back propagation, the error which is being generated, for example, I have x2, x1 is the original value, x2 is the generated value. So x2 minus x1 will give the error rating. Now, this error value will be given backward through the hidden layer and then again to the input. So there are two different kinds of neural networks that will be happening here. When it is going backward, it cannot jump directly over the hidden layer. So it has to send, the error can be sent only backward through the network. So now the weight be adjusted one by one from the last to the first time. So for example, from the output layer, it will pass on to the hidden layer first, then it has to go for the input layer. So now what will happen when it is being moving from step by step? What will happen? The weights which are being updated will be more effective, and also this will reduce the time in getting the exact desired output. So whenever we are going for any type of neural networks or optimization based neural networks, timing is the most important constraint for any type of problem. So now by this way, what will happen? This will improve the learning technique of the RNN. Why it is improving the learning? When we are making, for example, take this with respect to the human example. Human beings, as a human beings, whenever we are doing mistakes, from each and every mistake, we are learning one particular concept of the output, how we have to eradicate this mistake at the next step. But as a human beings, we cannot get corrected ourselves in a single step. The same thing will happen with the recurrent neural network with the back propagation. So what will happen whenever it is creating the error, the recurrent neural networks will start learning by itself, so that after n number of iterations, or maybe hundreds or thousands or 5,000 or 10,000 iterations, the system will perform very effectively, and then within a very short span of time, after these number of iterations, the system will give an exact output with a very less number of iterations. So when the iterations are getting less, automatically the time taken for execution of the particular problem will be very, very less. In this way, we can say this particularly optimized recurrent neural network will be effective or is effective than the other existing methods. So when coming for the research related thing, how it can be taken. So now, for example, I have method X, Y, Z. Now I am going with a new methodology in which an optimization technique can be integrated with this recurrent neural network. So recurrent neural network input can be optimized before giving. So that is the way where we are implementing the optimization techniques. So through that optimization techniques, the inputs can be, which means the main objective or the inputs can be optimized. So the required inputs can be given. So in this way, the backpropagation neural network will reduce the time in execution. When using alone of the backpropagation neural network, it will take a lot of time because it has to learn and then it has to give the output. But when integrating with the optimization technique, it will not take that much time because already it is optimized, so that the process will go very easily, and a smoother way we can obtain the desired outputs. Now, as I said, between the input layer and the hidden layer, the important concept is the updating of weights. So now how the weight can be updated, because it cannot be updated by keeping some values over there. So the basic formula which they have, which we have taken here is W is equal to W minus eta into del W. So now W is the normal weight which we are going to give, and then eta is the learning rate. So this learning rate will vary between 0.1 to 0.5 for many of the recurrent neural networks. The reason is only because early researchers, because still I am working on this neural networks regularly. So I will be taking the value from 0.1 to 0.5, because even we can take it as 0.0 to 0.0, because as it is mentioned in the bracket, we can see it is a small step for weight update. It cannot go beyond a certain value. So we have specified some threshold values for this particular learning rate, which can be 0.01 to 0.05, or I have taken for my problem, I am working on medical related problems. So I'll be taking from 0.1 to 0.5. Even I'm working on wireless sensor networks, intrusion detection. So in that case, I had taken 0.1 to 0.5 as the learning rate. It differs. So how it can be decided? So based upon the earlier research, you can take 5 different values of 0.1 to 0.5. First initialize 0.1, then see what is the output. 0.2, what is the output? 0.3, what is the output? So till 0.5, what is the output? So which is the threshold value which is reaching the exact desired value, so that that is the way where we are meeting the threshold value. Next is del W, which means the gradient value, the amount of change needed. For example, I can say, I can define the neural network. I can say, I can teach the neural network how much amount of the value has to be changed at the end value. For example, W1 minus W2 will give the del W, which means the difference between the weights. So now using this formula, the weights can be incremented, but it cannot be decremented at any point of time. If you decrement, what will happen? Again, the output will go below the desired value. So we have to be very clear in this. So this weight can be only incremented with respect to BPNN, which is backpropagation neural networks. So now again, as I said, this backpropagation neural network will learn by itself based upon the propagated and the updated value. So now we can, with the same backpropagation also, we can perform the forward propagation and backward propagation. Forward propagation in the sense, once the once the output is generated, I will go directly to the input, then to the hidden layer, then to the next generated output. But in backpropagation, from output to the hidden layer and then to the input layer. But in both the process, the weight updates will get continued till the exact output is obtained, and also based upon the total number of iterations only, the entire neural networks will make the system to be very effective in analyzing the generated outputs. After generating also, what we can do, we can check what out of the generated 100 or 200 or 1000 output values. I can't give 1000 outputs for one particular solution or problem. So I'll be able to identify only one best solution out of the recurrent neural network or any type of neural networks based on the classifications, because I am working on 3, 2, and 5 different classifications. It depends upon the input parameters value setting as well, because for each and every different kind of neural network, the parameters will differ. According to that, the learning rate will also get differ. Learning rate, as I said in the previous slide, this learning rate is very, very important in the neural network. If you choose the highest value, the desired output will go low, and also the output may not attain at a proper level. So now the recurrent neural network will train for multiple rounds. This is what I said, when the epochs are getting higher, which means the epoch numbers are increased, what will happen? The time complexity will get increased. As I said, when the time complexity is getting increased, the only advantage of this neural network is, even if the time complexity is more or the complexity system is more, but we can attain the very good output at the end stage. It will take a lot of time to make the recurrent neural network to train on multiple rounds. So, for example, we have taken a small example. For example, I have taken an apple as an image, as a symbol. So I am going to ask to the system or to any person, I am going to ask, what is this image, particular image? So now output can be anything, because I didn't make the system to learn till now. Now, what is the point here? I have given the apple, system has identified this as banana. So now this is, which means that as an user, as an end user, we know this is not the correct answer. Now what is error calculation? No, it is an apple, which means no is the answer. That's all. So now coming for BAP, how the BAP propagation will work. Now I am going to remember, which means the back propagation neural network will remember that it has made a mistake. Now I am going to update the weight. As a human being, our brain has to get updated, because our brain has to think that it is the error which has been done by us. So now I have to rectify this error. So what I will say to the brain, I have to learn more. I have to learn the characteristics of that particular image. Then only I'll be able to identify that image particularly, because we know the apple will be of round in shape, a little bit round, and then it will be red in color, and then I might have a green color leaf. But when going for banana, it will be lengthy and yellow in color. So now when these characteristics are made to learn, because for a kid, how we are making the kids to learn, like the same we have to make the neural network to learn. If you are giving an image, I have to teach the entire characteristics of that particular image, so that it cannot make the mistake the next time. Now, when the weight is updated, what is happening at the next time? We can see the child sees an apple and says exactly it is an apple. So now the same thing happens. It is for an image, I'm telling you. But when going for a data set, for numerical data set, how it can be done? So numerical data set will depends upon the input factors what are we have taken to identify the classifier output. So what are the input factors? For one particular problem statement, there may be 10 different input factors I can choose. So I have to make the system to learn all the 10 different parameters for all the number of samples. So by any type of combination, when it is coming out or when it is generating an output, it should say the exact answer. Till that, I have to train the network. So how it can be obtained? For each and every output, there will be a particular output state where it say whether that is right or wrong. If it is wrong, again it has to backpropagate. Again it has to update. Again it has to give one result. So now, where and why it is being used? One thing is, as I said, it needs the past value, present and the future. It is like a normal sequential data transformation which is happening in the digital electronics. So now, in the same way, the recurrent neural network has to learn the data from past stored value and then what is a present value and what is a future value. So it has to remember the past information. If not, the recurrent neural network is of no use. So now, when using backpropagation through the timing, because timing is very important, as I said, again, when the output is being fed into the hidden layer and the input layer, it cannot take more time. It should not take more time. Not it cannot, it should not take more time. Because if it takes more time, what will happen? As the digital electronics, how the states are being transferred from one state to another state, it for some time period, it will wait. If it does not, it will say it as a no state or improper state. It will give a cross mark over it, as we have seen the truth table. Like the same in the neural network, what will happen? It will wait for some time to analyze the information, whatever it has. If it is not able to go for it, it will go for next iteration automatically. It will not wait for the output to be generated. This is one important thing in neural network which we have to learn. Now, unlike feed-forward networks, RNN can process time-dependent data. So there are many different types of data sets available, which is the time series dependent data and time dependent and series dependent. So now this feed-forward neural network, likewise, RNN can also process the time dependent in the sense based on the timing of the input values, whatever we are processing or the output is getting generated, I can go for this particular effective neural network can be utilized by using the time dependent, because none of the other network can process with respect to time dependent. So the next is where it can be used. So as I said, the previous values has to be stored. The current value has to be known. Then only the future value can be corrected, which means it can be generated or it can be identified. The first thing is speech recognition. So we all know currently or the latest we are using the Alexa in our homes or any other types of automated voice recorders. So now what they will do earlier, I can take chatbot as an example. Leave that is the second example which I have given. So fine, going for Alexa because speech recognition. So earlier, whatever the inputs that has to be outputs has to be generated, according to that, they would have done the large language models and then the corresponding combination of inputs has to be stored in the machine. Then only based on the prompt which I am going to give for the machine or the Alexa, it will give the answer. Because without storing, it cannot give. It is not a human brain which can think at instant. It can think only upon the based upon the input values what are we have chosen. The next is text predictions and chatbots. Text prediction, for example, like in Tamil, we have RIEE. We can use this because recently I have worked on this particular research area. We have identified the text recognition for blind people. So Tamil, R to AK. So we have taken this particular proper Tamil words and I had given it as an image to the neural networks. And now what will happen for the blind people, on what basis they can recognize the text? In mobile, they have a point at the keypad number 5. But when going for the text prediction, how it can be done? So still that research is going on with our scholars and as well as our faculty members. So they are keenly working on this. And then chatbots is an example. So we are going to any banking websites or any, for example, your college website, you can take your college website. So there will be an automatic chatbot, how they will assist us. So whenever you are giving a question to them, it will give an automated answer. The same question can be given by another person. The answer can be different because this is the way where LLM will work. Everyone knows about this ChatGPT, right? So this is simply as a chatbot. That's all. AI assistant will work only according to the prompts, whatever you are giving. But each and every time the prompt can be same, but the output can be different. The same way BPNN also will work. Stock price forecasting. So yesterday the stock price of X company is this one. Today it is this one. What will be tomorrow? So the forecasting things, weather forecasting, that can also be an example. machine translation, which means Google Translator. So if you go to normal Google and give a Google Translator, if I give any sentence, that can translate to any language, because already it has been programmed, it has been given to the machine stating that if this input is given, this should be the output. For Google Translator, the concept is different, which means that which means the exact answer will not be given, but the LLM or the program behind that LLM is very, very complex in Google Translator. Any inputs, whatever you give, it can give an output in any other languages. So in this way, they have given the machine translation for the Google Translator. So now this is the way where these are few examples of this recurrent neural networks, how it can work. And then, so coming for the end, I would like to complete within the time period which has been given. So this RNN processes sequential data and remembers the past inputs. So most important point which you have to remember in this neural networks is recurrent neural networks is sequential data is mandatory, because each and everything is interlinked. If one chain gets break, it cannot process. This is the first point we have to know about in RNN. Coming for back propagation through time, helps adjust weights over the time period. So within a very short period of time, the weights will be updated so that the next output can be generated very easily. So as I said, the previous slide, the applications can be like speech, text, finance, and all AI applications will be depending only upon this recurrent neural network. And my personal opinion, for any type of research activity and problem statements, this recurrent neural network and back propagation is a very effective tool for analyzing the outputs. So I would like to stop here. I think I had given my best. So if you have any doubts, you can ask here. So thank you. Two to three people has given comments on the presentation. Because I said a very short time, really, I wanted to complete with the 30 minutes
Thank
of
you,
time.
sir, for the valuable session.
Thank you very much, sir.
The session 2 attendance and feedback form will be posted now at chat box. Once again, I repeat, the attendance will be monitored with the feedback form. Once again, I repeat, kindly fill the attendance and feedback form. There will be only one form for both attendance and feedback.
The PPT will be shared by the concerned person, because the PPT is available with them as well.
Okay, sir.
Yeah. Thank you, sir. Thank you very much to all the participants. Thank you.
Thank you, participants. Stay tuned. We will meet tomorrow.